Hey guys. So before warned, this talk contains some live coding, so set your expectations to low. I'm a software engineer at Equal Experts, and we're a worldwide network of mostly senior consultants and technologists. And we are very keen on agile methodologies, and so we practice TDD extensively. And we've been exploring all facets of basically what it means to test software and the tools that we can use. So if you are interested in testing, or if you currently have a background on TDD, hopefully this will bring you some awareness of a slightly different way to write your tests. And if you already know property-based testing, then feel free to join in the conversation and provide feedback. So just a little intro for those of you who don't test. And being Portugal, sometimes that's not always the best or the practice that we adopt. So just for a little bit of show of hands. Who writes tests on their software? Okay, pretty good. So what do you test? You want to prevent regressions. You want to document your code, because tests are specs, right? Or specifications. And if you adopt TDD, you write your test before you dive into the implementation, then it's also a design aid. And it narrows the focus of what you're developing. And gives you QA, and if you have a CI pipeline, it runs tests and makes sure that only stuff that's not broken gets to live. So how do we test? So there are a number of tools and strategies that are at our disposal. If you use a typed language, usually the compiler will give you the first line of defense against bugs by checking types. And if something goes wrong, you get type errors, and you go and fix your code. There's some slight improvement on this is automated linting. So you have a specific set of rules that you want to enforce on your code, something that's not worth checking manually because it's so easy, so you put it into an automated process rather than waste developer time on code review or pairing to fix these issues. It's not really testing, or it's not the best way to test, but it's something. You can test manually if you're a chump, or you can automate your tests by writing unit or behavior-driven development tests. And within this subset, you've got two approaches. One is what you'll probably think is the traditional way of having an example that you want to test. So you provide a set of inputs, and you expect an output to come out of your function or module or whatever. And there's something called generative or property-based testing. And this works by generating the inputs in an almost random fashion, and you test based on this randomized inputs. And this is what the talk will be about. And OK, so example-based testing, and just to give you an overview of why property-based testing exists, is that example-based testing is good for most cases, but sometimes you feel it's not enough, or you feel that there are a few issues that could be improved in it, such as what test cases are significant? How many tests do I need to write? How much coverage is enough? So do I have to check all sorts of, say you're writing a function that takes a number, do you test a negative, a zero, a positive number, the biggest one, the smallest one, anything in between? Where does it stop, actually? And at some point, are you maintaining your relevant tests? And how much work would it take to change if the specifications change? So to address these concerns, there's something called property-based testing. So instead of testing individual cases, instead of you providing, say, here's a negative number, I expect this back, you test the general behavior of your system. So one of the things that's at the core of property-based testing is a generator. So if you've heard of fuzzy testing, it's basically that. So there's a generator that spits out more or less random whatevers. So it could be a number, it could be booleans, strings, arrays, whatever. And most, just before we get into detail on generators, just the ability to generate these values or these inputs automatically and randomly, this is already very valuable, because you can test certain behaviors without having to dive into more complicated stuff. So if I provide a number, it should always work. If I provide a string, it should always work. Or if I provide something that a type that's unexpected, it should break. And you can test these things in a much more concise fashion using this. You don't have to think about all the input cases. So most frameworks, most property-based testing frameworks will provide you a number of generators for all the primitives. So if you need random integers or random floats or random natural numbers greater than 0, or strings or lists of any of the types that I've already mentioned, they usually come out of the box from your property-based testing framework. So what's a property? So if you let's take a simple example, that's addition. If you remember your math classes, you'll remember that addition has a number of properties, the addition operator. And they're this, basically. So there's commutativity that says that x plus y equals y plus x. So the order of the operands doesn't matter. And this is a property. And this is what you're going to test when you write a property-based test. You don't provide 1 plus 1 and expect 2, because you don't know what the inputs are. They're being randomly generated. So you have to turn your thinking around a bit and think about the whole behavior and compare it with either something that doesn't change or something that depends on the function itself. I'm going to give you a few examples later on of strategies and to find properties that you can test. But this makes you think a little bit harder about the problem that you're trying to solve when you write these tests. Okay, so a little bit of live coding. This is JSVerify. It's a JavaScript and TypeScript framework. It gives you a number of functions and generators. So what you see here, integer is a generator, and these are basically your testing functions, your asserts. There are two ways to express a test in JSVerify. So the primitives check and for all will work on every framework that you have. That's pretty much universal. But if you use something like Mocha or Jest or any framework that provides a global it function, then there's a property function that wraps that it and gives you a more concise syntax for these tests. And this is what we're going to use because we don't want to write too much. So we have the first test done. That's commutativity. So what you say that there's a property, and you give it a name or descriptor, anything, and then you provide a list of generators. In this case, we want to generate 2 integers to provide the function. So you put in the integer twice, and it will generate 2 different numbers. And then you put in a function that should return true or false. If it returns false, then the property test failed. If it returns true, then the property test passed. So it should be true that add A, B should be the same as add B, A. And it is. Tests run, it passes. So let's write another property. So the other property of addition is, by the way, I'm using TypeScript, so yay for code completion. In this case, we want 3 integers, so let's put it in 3 times. Sorry. A, B, and C, and associativity states that A plus B plus C should be always the same as A, B, and C. So it doesn't matter what order you the operand works. And again, it will pass the test. Of course, I've already written the function, so this is not TDD. So what other properties are there for addition? There's identity. And there's identity, and identity, you only need 1, because the identity is any number plus 0 should be itself. So you only invoke it. The generator is an object. It contains the number of methods that then generate your number. So this is used internally. We'll learn how to create custom generators a little bit later on.
Sorry.
Sure.
Line 4 is supposed to be multiplying.
Is it? We'll see. Good catch, though. So add A and 0 should be the same thing as A. And of course, it runs and it fails because, failed after 2 tests and 3 shrinks. I'll talk about what the shrink is. It's not a psychiatrist. And yeah, it failed because, like Zé pointed out, this is not the right operand. Yeah. So you get the idea. And basically, you describe it not in terms of, an expected output, but you try to play around with the problem space and try to figure, more or less creative ways how to test your function without actually testing explicit outputs. Okay, so you've seen a little bit. I'll break this again. You've seen that it failed. And this gives you a few useful outputs. So first it says that it failed after any number of tests. So by default, JSVerify will create 100 random things for you, and it will test them all. So there's some considerations in terms of performance when you're writing these tests, because every property that you're testing is the same as 100 unit tests. So if you're doing TDD, you want fast feedback, don't go crazy on testing properties, because it might slow down your tests. And so it tells you how many tests it tried to run, and we'll get to the shrinks in a bit. And it also tells you something that's the RNG state, because these values are more or less random. I'm saying more or less randomly generated because there's a bias in the generators. Generators will always try to generate values for edge cases first. Like if you are generating a random string, it will always generate an empty string first, or a string with the maximum allowed number of characters, or for a number, it will try 0, 1, -1, the max integer and the min integer. So it will go for this first, and then the randomizer will kick in and give you all the others. And it will also give you a counterexample, and the counterexample is the number that was generated that failed this test. The RNG state is useful because you may want to reproduce the exact test that failed here. You want to avoid Heisenbugs, stuff that passes once but then fails next time you run it. And so you can take the hash or the little string on the RNG state and feed it to your test. There's an object that the property function takes, and you can pass it a custom RNG state, and it will always replicate this sequence of numbers. So okay, back to our edition. So this is all the properties in JavaScript. So what can you test? So you've seen a few examples. So you've seen this, different paths, same goal. There are multiple ways to get to the same end result. This is a property that you can test. If you want to think in terms of, say, navigation, going north and then going west should be the same as going west and going north. And if you can map this kind of thought into your system, the system that you want to test, you can write a property-based test based on this. So multiple ways to do the same thing. There are also round-trip tests. These are particularly useful if you're writing stuff like serialization and deserialization, stuff that you can do and undo, getters and setters. So you set a value, you should get that value. If you serialize JSON, you should parse the original value back when you get that JSON string. So in no case are you required to think about explicit outputs. You're just thinking about how the system behaves. There are invariants. Stuff that never changes about the input. So if you're sorting a list, the list will always have the same size. Different ordering, but same size, same length. Should have the same, maybe same type, if you're writing a test for a language that doesn't support types. Or also the same thing for a filter. Stuff that doesn't change at all, so idempotence. So if you sort a list twice, it's not going to add anything to what you did before. The same thing for setters. Set the same value twice, it's not going to change the end result. And filters, if you filter a list by the same criteria, it's not going to change. There's an interesting use case for property-based testing. If you're rewriting code and you want to make sure that the new code that you wrote adheres to the same specs. So for instance, if you're, and this is great even if you don't have tests on the original system and you just want to compare two functions or two modules or even two whole applications, because you can apply this to assertions on user tests, on automated user tests. So say you have a legacy function that behaves in a certain way, you're trying to guess how it works. You can use property-based testing to feed both the old legacy function and your new refactor the same inputs and expect the same output back. And this is really, really useful and a great use case for property-based testing. That's not to do with CI or TDD. And of course, hopefully, you should be writing tests for the new code. Also, if you're doing single and multi-threaded implementations, you want to make sure that they behave the same. So you feed one and the other the same inputs and expect the same output back. Or you're doing an optimized version, and you can even write a property that says the old function should always be slower than the new one to make sure that it's actually optimized. So okay. FizzBuzz is one of our testing exercises that we give candidates. So take notes if you think of. By the way, we're hiring, and if you like tests, we definitely want you. Okay, so FizzBuzz. So I've already implemented it here, so I don't have to think too much about it. And now FizzBuzz as, let me just silence this so we don't get any noise. So what are the properties of FizzBuzz? So we already looked at some of the strategies. So what can we test on FizzBuzz? So if you know the problem, or if you don't, I'll tell you. So FizzBuzz takes a range of numbers, and it generates a list that's a series of numbers between the values in that range, with a few exceptions. If the number is a multiple of 3, it should be replaced by fizz. If it's a multiple of 5, it should be replaced by buzz. And if it's a multiple of 15, it should be replaced by fizz buzz. And it's a stupid exercise, but you won't believe the amount of people who fail it. But it's a pretty good example of how you can use this sort of testing to test fizz buzz. So the more obvious one should be maybe something to do with invariance. If you're providing a range of numbers, you should get a list that's the size of the distance between those two numbers. So there are plenty of properties you can think of. We've gathered a few over time. So it should be, this is the Euclidean distance between the two numbers you provide. So and it passes. If I were to break this somehow, change the range, it would immediately tell you. I tried 0, 0, and it failed with that. And it gives you the counterexample and the RNG state and everything. It also gives you, again, the shrinks. And we'll get to that in a moment. So now you want to test something that's a little bit more complicated. And that's what's a multiple. And you could say, you could give the fizzbuzz function a number and multiply it by 3. But if the test were to fail, it's not going to give you some very useful output. So let me give you an example of that. And I'm going to fail this on purpose so you can see the output. So for the fizz one, it's still the same. We only need one because we're going to look at a single value of the array. We already covered the length of the array, so let's focus on that. And it's not the length. And the fizzbuzz, it should give you an array back, so you look at the first element of that array, and it should be fizz. And of course, this is a times 3, and this is a times 3 plus 1. And it failed. And counterexample, it's not a very useful counterexample, sorry. Let me change this to should contain fizz. Because if it's a multiple of 15, like 0 is, it should start with fizz. Okay, and it failed. It failed on 1, even though 1 isn't really being tested. And this is because this is not a very good way to approach this. You actually need something that generates a multiple rather than an integer, because the integer is what you're going to get in the counterexample. You want something that's an actual multiple. I have a little helper function here that what it does is it takes the integer generator and then applies a map to it. And what it does is it multiplies that number and gives it back. It's actually two functions if you look at it. So the first function is the generator function. Takes one of the integers, multiplies it by 3, and gives it, and that's your number that will appear here. I'll take this out. It's still going to fail, but it's now going to give you 3 failed, not 1. And the second one is a shrinking function. So the shrinking function is what allows you to get that 3. And what it does is it's just that. It shrinks a value. And it should be the right inverse of the first function that you provide, and it's basically the reverse of what you're doing. So if you're multiplying by 3 on the first function, you divide by 3 on the shrink, and the shrinker gives you the smallest possible value that still fails the test. And this is very useful when you're debugging your tests, because if this were to generate, I don't know, 10,000,007, why is that number meaningful? It would be meaningful in that it failed the test, but it's not really useful if you're debugging the code. So you have the shrinking function, which is applied by the property-based testing library, and brings it down to the smallest possible value. Either it's a number or a list, smallest possible string, that still fails the test. Let me give you an example of this. So there are 2 ways to create an arbitrary generator on JSVerify. If you don't want or you can't find a way to shrink values, you can sort of cheat and use bless to bless a standard normal JavaScript object with a generated method. And in this case, we have a datetime generator. And datetime generator takes the new date, and actually takes a number and converts it to date, and then it multiplies it by an hour just to make it more interesting. This net is another normal generator that's provided by JSVerify. It creates positive numbers, basically. You can give it a range of allowed values. So if you, in this case, it's max safe integer, but if you want to generate natural numbers in a range, you can say net's 100, and it will give you numbers between 0 and 100. And basically, you create a new object like this. So when you run this test, let me just silence the test that I've been writing, so you get a clean output. And it failed. I intentionally broke this because I'm looking for dates that are in the past. And it gives you a date that failed. It's in the future, and it's well in the future. It's the year 2172. Why is this meaningful? So let's look at an alternative. Using smap and providing a shrink function, we're basically doing the inverse of what we did above. We take the date, convert it to a number, and then divide by 3,600 seconds. And it's going to give you a slightly different output. And you're going to notice that it failed the test, but it always fails with the current date, because that's the smallest possible date that fails the test that you're looking at. You only want dates in the past, and the current date fails. So no matter how many times you run this, no matter what the RNG state is, you're going to get consistent, or at least useful, counterexamples of what failed the test. Another example, in this case, we're generating a list. I have a count function that's intentionally broken. It gives infinity on any list that's bigger than 3. If you have a test without a shrinker, it's going to say, well, this list of 14 elements failed. Wait, this list of 146 elements failed, and so on. If you have a huge list or a huge object, testing this is going to be a pain in the butt. But if you use a shrinker, then it's always going to say, this list of 3 elements fails the test, no matter how many times you run it. The shrinker is able to find the smallest possible value. And here, in this case, our generator is a list, is a range creator, so it creates something, and then the inverse takes an array and gives you the total count, gives you the length. That's the inverse of the first one. So okay, that's the shrinker, and that's why we're using it here, so that we get a proper counterexample when we run this test and the test fails. So it should still be broken, so I'm going to fix this. So it's pretty much the same for buzz and fizzbuzz. So I'm not going to do those because they're a little bit boring now. There's another one. So for any number that's not fizz, that's not a multiple of 3 or a multiple of 5, you want to output the original number. That's the other test that you want to write. I'm going to break this again. And for this, JSVerify gives you a helper function called suchThat. And suchThat applies a filter to your generator, and it basically filters all the stuff that you don't want to use. Again, I have a small wrapper around suchThat that I can use here. And basically, you want a number that's not divisible by 3 or 5. And so the suchThat thing, it takes an arbitrary. In this case, it could be one of the multiples. It could be just an integer. And you say that whenever you divide it by whenever you divide it by anything, the remainder should always be greater than 0. I have an example here for simple integer. I'm going to copy it. And so I'm using the wrapper that I just did, and I'm saying it's any integer, but it has to be indivisible by 3 and indivisible by 5. It should cover all the exceptions, and it should always be the number itself. Of course, I broke the test. It's going to fail for 1. Again, it's the smallest possible value that fails, because 0 is not is filtered out by suchThat. And when I fix my implementation, it should pass. So shrinkers and filters, they exist for when a test fails, etc., etc. So another interesting use case, you can pretty much do anything you want with generators. So these were pretty simple, basic examples of custom generators, creating multiples. But using JSVerify, you can even create entire objects. So this creates a user object, for instance, a person object. And there's a record generator on JSVerify. And then you can use, say, for one key, you want a random string, and for the name, last name, you want another random string. For the age, you want a random number. And you can even have a custom generator that gives you a random email address. And then you can use it combined with suchThat. For instance, you're testing like an adult site, and you want to make sure that only users that are above the age of 18 are able to access it. You can write an arbitrary like that, and that generates arbitrary adult users. Language support. So I've given you the examples in JavaScript or TypeScript. The granddaddy of all this property-based testing thing is actually Haskell, and that's the original library, Quick Check. There's been implementations of this in pretty much every major functional language, F#, Scala, Swift, Elm, and they're pretty much direct implementations or direct inheritors of the original one. And of course, Java's a quick test one too, and JavaScript as JSVerify. There's an older one. JSVerify is not the original one, but it's actually based on JSCheck, which was created by Douglas Crockford. But it's been pretty much abandoned, so these guys picked it up. There are a couple of others, but they're not as fleshed out as JSVerify. And even JSVerify isn't as fleshed out as, say, Quick Check or Scala Check. For really, there's some things that you can do in Scala check out of the box without having to worry about creating your custom generators. Stuff that, like actions that contain an internal state that you can check. So suppose you're writing a website that has a login form and a logout option. You can write a generator for sequences of actions, and then you can check that after a random sequence of action, you can check the internal state of this on the testing framework, that it should match whatever is on the page. So these are more advanced use cases. And yeah, so to recap, property-based testings improve the coverage of your tests by using randomized generated inputs. They should complement your traditional example-based tests. There's a performance argument against using property-based testing. There's also an overhead about thinking about your problem. It's useful to think about your problem, but if your example-based, your normal tests cover the solution, it should be fine. They're not supposed to be a full replacement anyway. They do require changing how you think about tests. So yeah, you're not looking at explicit outputs. You're thinking about behavior. And yeah, thank you.